Okay, so let's take a look at the last part of this chapter, which deals with genetic mutations. So a genetic mutation is a change in the DNA nucleotide sequence. So if you change the genetic sequence of the DNA, you're going to change the codon sequence, which can change the amino acid sequence. But if you change the amino acid sequence, you're going to change the protein. And in most cases, we're going to make a non-functional protein. All right? So the first type is called a frameshift mutation. And this is where one or more nucleotides are either inserted or deleted from the DNA. All right? So this is showing a frameshift mutation here. So here is what our sequence was. And now when you put an extra one in, it shifts everything over one nucleotide. So in doing so, we will get a completely new sequence. All right? So that's what happens in a frameshift mutation. So you get a completely new sequence of amino acids, so you get a completely new protein. In most cases, this is non-functional. Next is a point mutation, so let's go back to here. So looking at a point mutation, this is a change in a specific nucleotide and thus a change in a specific codon. So the first is called a silent mutation. This is in a silent mutation, the new codon that you make still codes for the same amino acid. So if it was CUC and it gets changed to CUA, well, it's still leucine, so you have the same amino acid there. Next is a nonsense mutation. So, with the new amino acid, with that same amino acid, you still make the same protein. So that's why we call it a silent mutation. Next is a nonsense mutation. And so here, the new nucleotide is a stop codon. All right? So if we think about this, as I mentioned earlier, is that these proteins can be hundreds to even thousands of amino acids in length. And if we put a stop codon somewhere in there, it's going to shorten that protein up and probably make it non-functional. Lastly is a missense mutation, and that's where the new mutation codes for a different amino acid. All right? So let's get to an example of a point mutation in which we have something dramatically different. All right? So this is showing hemoglobin. Hemoglobin is the protein that transports oxygen in our blood. And so this is the normal type, all right? And so here's the sequence of CTC, which gives us the messenger RNA of GAG, and we get glutamate, and that gives us normal hemoglobin. Well, if you just change that T to an A, now we have a different messenger RNA of GUG there, which gives us a different amino acid called valine. And valine changes the shape of a normal hemoglobin to a sickle cell hemoglobin. So this is how important a point mutation can be. In most cases, we get something very similar to the protein that we once had. Here, we get something a lot different. So causes here, causes for this. One is just bad luck. A mismatched nucleotide can be put in during DNA replication. Now, if this occurs in one of your somatic cells, a typical body cell, then that's a mutation that you're going to have. If this occurs in one of your gametic cells, then that's a mutation that one of your offspring would have. Another thing, this can be caused by mutagen. So that's a substance that causes a mutation. So basically what mutagens do is they break the DNA, and the DNA is put back together incorrectly. So mutations can be such things as radiation, a carcinogen, any cancer-causing agent is also a mutagen, like smoking, all right? We know ultraviolet radiation can do this, all right? And what we really want to do is we want to lower our exposure to mutagens. Mutagens are constantly in the environment. There's these things called background radiation. So radiation comes out from the ground, cosmic rays from outer space, sunlight from ultraviolet radiation from the sun. That's what we call our background radiation. And so what we want to do is we want to limit further exposure. So our DNA is constantly being broken. We're constantly repairing it, but we want to limit how much that occurs. All right? So if you get an X-ray done, for your teeth, that small amount of X-ray exposure is probably not enough to cause a cancer on you. But if you're an X-ray tech, right, or a dental hygienist, and you're constantly sitting there day after day dealing with those X-rays, that could cause a mutation in you, which can lead to cancers. And this is what happened to Rosalind Franklin in X-ray chromophotography that she did, is that she was constantly exposed to these X-rays, and she died of ovarian cancer at a very young age of 37.